Hello everyone, a warm welcome to my dear students. Today we'll be discussing on a subject digital electronics and logic design. So in this we'll be studying few topics from unit number 4, which is an algorithmic state machine and programmable logic devices, that is an ASM and an PLDs. So first of all, let's see what do you mean by an PLD, which is an programmable logic devices. These are nothing but a collection of integrated circuits which are configured to perform various logical functions. It plays a very important role in order to develop an automated digital system to improve process flexibility and efficiency. Your programmable means defining a function that can be performed multiple times without human intervention. And PLDs generally has an and array matrix and an or array matrix. Okay, so let's understand what do we mean by an array logic or an array matrix. Now a PLD may have 100 or millions of gates interconnected through 100 or 1000 to internal paths. Now, in order to show the internal logic diagram in a concise form, it is necessary to employ a special gate symbology which is called as an array logic. Let's see how to draw an array logic of an AND gate and an OR gate. Now here you can see this is an AND gate having multiple input and a single output. This is a conventional symbol which we have used till now, okay, in order to design a combinational circuit or an sequential circuit. Now for designing a circuit which is based on PLDs, here what you do is, since I have a multiple input over here, what I'll do, here we have a single connection and then different multiple inputs are connected to the same wire or a same input channel. So this is what, this is a collection of different inputs, that is an, it is an array, right? Array of different inputs and a single output. Similarly for array, now sorry, for OR array will have the same logic. Now, there are three kinds of PLDs. First is PROM, which stands for Programmable Read-Only Memory, PAL, that is an Programmable Array Logic, and PLA, that is an Programmable Logic Array. The process of entering the information into these devices is known as programming. Now, programming doesn't mean that you'll have to use a different programming language which is available like C, Java, Python, etc. Here in digital electronics, programming means we are talking about an hardware programming and not an software programming. Okay. So let's start with our first type, that is an PLA, which stands for Programmable Logic Array. Okay. So it contains an array matrix of or an AND whose configuration is done as per the need of application. Okay, and in PLA it allows both AND matrix and OR matrix to program. Okay, you'll understand the difference between PLA and PAL as we go further. PLA allows both AND matrix and OR matrix to be programmed, whereas PAL allows only programming of OR matrix, whereas programming of AND matrix, whereas OR matrix is fixed. Okay. So industrial electronic PLAs are used to design and implement a variety of complex combinational circuits. However, some PLA also have a memory element, hence they can be used to implement sequential circuit as well, along with the combinational circuit. So this is a general block diagram of an PLA where we have input buffer at the input side, we have an output buffer from where we can get the output, and in between input and output buffer we have an AND matrix or matrix and an invert or non-invert matrix. Let's see all these blocks in detail. So input buffer, the symbol of input buffer is like this. We have a NOT gate. Okay, a bubble is given over here. That means if my input is X, I'll get my first output as an X, and the output which is coming out of bubble will be your complemented output or an inverted output. So we'll get your X bar if your input is X. So it is used in PLA to avoid the loading effect on the source that drives the input. An array is used to generate the product term. Similarly, an OR array is used to generate the sum term. And invert or non-invert matrix, it is a buffer used in PLA to set the output to active high or active low. An output buffer is used at the output side. It is mainly provided to increase the driving capability of the programmable logic array. So there can be a theory question also. So if a theory question comes, you'll have to write some theory about PLA. Along with that, you'll have to draw this block diagram and explain each block in detail. And after that, if a numerical comes on PLA, there are different steps. That is, there are basically 5 steps to solve the problem on PLA. First step is to draw a program table which shows the input, product terms and output. Second step is to design the AND matrix that can generate the desired product term. Third step is to design the OR matrix that can generate the desired output. Fourth step is to design the invert or non-invert matrix to set the active low or active high output. And the last step is to finally draw a PLA using PLA program table. So let's take first example, that is to design a full adder circuit using programmable logic array PLE. So everybody knows at this stage what do you mean by full adder? It has 3 inputs and 2 outputs, right? So here I have directly included a truth table of an full adder where we have 3 inputs A, B, C, and it has 2 outputs S and C out. That is, H stands for sum and C out stands for carry. Now since there are 3 inputs, we'll have combination starting from 0 to 7. Okay, so the binary number of 0 is 000, binary number of 1 is 001, and binary number of 7 is 111. Now how we'll get this table? Yes, so this is S stands for sum, so 0 plus 0 is 0, 0 plus 0 is 0, and C out is 0. Now let's consider this example where we have 0 plus 1, 1 plus 1 is sum, 0, carry 1. So in this way we have filled sum and carry outputs in the truth table. Now this is our equation where we have minterms. The minterms came from this table. Wherever the sum is high, that binary number we have that equivalent decimal number of that binary number we have included over here. That is, here I have some output as 1. So the binary number is 001 and equivalent decimal number of it will be 1. The decimal number for this output is, yes, this is 010. So the decimal number is 2. Next is, here we have one more 1. The binary number is 100. So 100 represents which decimal number? 4. This is, here also we have a high output. So the equivalent binary number of that output is 111 and the decimal number of 111 is 7. So we have included 7 over here. Okay. Similarly, find out the minterms for this table C out, which is summation M 3, 5, 6 and 7. After that we draw a K map of it where we get a reduced equation using an K map. Okay, so this is the equation for my sum and this is the equation for carry. I think there is no need to explain this K map because it is already there in the first unit. So let's move forward. So depending on this equation, what we did is, next is consider all these equations. So how many terms are there in sum? 1, 2, 3 and 4, and in carry 3. So 4 plus 3 is 5, 6 and 7. Okay, so here how to draw program table? Here we have 1 to 7 product terms. Write all the product terms which we got from the earlier equation. Okay, so these are all the product terms. Here I have drawn an input table and an output table. Okay, so now first equation is A bar B C in bar. So this is an complemented term. So under A I have written 0. Now B is not complemented. So here write down 1. This is an C in bar. So 0. Next A bar B bar C in. A bar and B bar. So 0 0. C in 1. A B bar C in bar. So this is 1 0 0. Okay, and how to fill, similarly you have to fill remaining also. And what to do in this column is, this is an equation of sum term a bar b c in bar. This one a bar b c in bar, a bar b bar c in plus a b bar c in bar. All these terms are from sum equations. So above, in front of all this term we'll write sum as 111. Okay, and the remaining three terms are from carry equations. So here don't write anything. See out may you have to write 1111. Okay, so the last step is we'll have to draw a PLA circuit diagram. Okay, so here we have a three inputs A, B, C in, and two outputs sum and carry. So we have drawn an input buffer, okay, of A, B and C in. Here this terminal will give you output A and this terminal will give you output A bar. Similarly B, B bar, C, C bar. Okay, now let's, and also draw sum and carry S and C out. Okay, so how many product terms do we have? We have 7 of them. Okay, so draw 7 product terms P1 to P7. Actually this is not required, you'll have to draw only P1 to P7. Okay, now my first term is A bar B C in bar. So I'll place across on A bar B C in bar, and this is the product term of sum. So I'll make a crossover here and connect it to this sum or gate. Okay, next term is A bar B bar C in. So this is my A bar B bar C in, which is an second product term which belongs to my sum equation. So I put a crossover here. Okay, so depending upon the equation, whichever is your term available in your equation, just mark a crossover there, and across your output side, whichever is the product term, either it is of sum or carry, cross it over there. So for sum we had a 4 product terms, whereas for carry we had 3 terms. Okay, so let's consider second example. In this we have two functions f1 and f2, where they have directly given us the minterms 3, 5 and 7, and f2 is nothing but 4, 5 and 7. So here directly draw a truth table. Okay, so my first minterm is 3, 5, my first function which is having minterm 3, 5 and 7. So under f1 I'll place 1 which is available, that is 3 is given as a minterm. So 0, 1, 1, 1, 0, 1, 1 represents binary number for decimal number 3. So I place 1 over here. Okay, then 5 and 7. For function f2, 4, 5 and 7 are given. So 4, 5 and 7 we have placed 1. After that draw a K-map, find out the equation. According to the schema, our first equation AC plus BC, F2 is A, B bar plus AC. And then a program table, place all the product terms over here, AC, BC and A, B bar. AC, BC, A, B bar. AC is common, so there is no need to repeating that term over here. Okay. So in program table we have product term column, an input column and an output column. Input column we have A, B and C. Output we have two functions given, F1 and F2. So my first term is AC. So under A I have written 1, under C 1, which is a function of F1 and F2 also. Yes, two functions were given at the input side. So F1 also contains AC and F2 also contains AC term. Yes, so here both the inputs will be high over here. Next is BC. BC belongs to which function? F1. Here BC is not available. So under F1 I'll place 1 over here. Okay, and it is BC, so 1 1. It is an A, third term is A B bar. So A B bars. So here place 0, which is a function of F2. And after that draw a logic diagram in the same manner which we did earlier, where we'll have three inputs A, B and C. This is an input buffer. From this terminal we'll get A, from this terminal we'll get A bar, B, B bar, C, C bar. Okay, so we have three product term A, C, B, C and A, B bar. This is A and C. So under A, place a cross mark. Under C, place a cross mark. After that, one AND gate, and the output of it is a function of AC is a function of both. And this also we saw AC is a function of both. Okay. So under F1 and will place a cross, and also under F2. Next is BC, which is a product term of function F1. A B bar is a function of F2. So next is programmable array logic, which is an PAL. Now programmable array logic, in this we can program an AND array, whereas OR array is fixed. Okay, in PLA both were programmable, but in PAL only AND array is programmable and OR array is fixed. Since PAL are easily manufacturable and less expensive, they are popularly in practical application. This is the block diagram of it, and the method of solving the numerical is the same. The only difference is what? Here AND array are programmable, so place a cross, and OR array is fixed, so place a dot over here. Thank you.